So we have, of course, all these phenomena. We know nature works, but what are the theoretical ideas underpinning this? And the theme of unification is a wonderful one, because we have seen actually that there's the incredible power of ideas to unify many, many different physical phenomena. And actually, the Institute for Advanced Study where I work has kind of a motto which is truth and beauty. And that actually is a very interesting philosophical theme. And great scientists have spoken about this. For instance, there's a wonderful quote by Hermann Weyl that if he had to choose, he would often choose beauty, just the power of ideas. Or Paul Dirac, who was even more adamant that it's more important for equations to be beautiful than to fit experiments. Although if your theory doesn't really quite work in practice, it certainly looks less beautiful, I would say. But then there are another perspective. I like the remark of John Wheeler, a great physicist, black holes, nuclear physics, worked on that any law, when pushed to the extreme, is kind of approximate and statistical. Or Francis Crick from Watson and Crick fame, a theory that explains all the facts is wrong because usually some of the facts are wrong. So that kind of tension between beautiful ideas and the conflict with reality is something we'll see many times. And of course, I want to start with a little parable, which is a story from the old Greeks. So the old Greeks had their own theory of everything based on mathematics. In fact, for them, mathematics, the most beautiful thing were these 5 geometrical objects, the platonic solids, the most perfect objects in math. And they had a theory of everything which was loosely based on the equation 4 + 1 = 5, because the 4 elements out of which they thought everything was made of corresponded to these 5 objects. You see kind of the square was kind of nice. You can build out matter out of it, so that would be the element Earth. The tetrahedron was kind of pointed, so it would hurt, so that would be fire. And then there was the 5th element, which was the dodecahedron, and actually they felt that stood for all the matter outside the Earth. That was Plato's conjecture. So the planets, the stars, the heavens would be made out of a different kind of material. And in fact, if you go even in art history, you often see this beautiful figure of the dodecahedron, and it's kind of symbolizing, I would say, kind of metaphysics. The things that actually we are hearing about today so much. Now, in fact, it's even here in the old meeting room of the Dutch Parliament, and I was just the other day reading some description of it in a newspaper, said, well, is it quite appropriate to have a soccer ball hanging in this hallowed grounds? But, so we went from the structure of the universe to soccer. But I'm telling the story because I want to tell a story about Kepler. Kepler, a famous, of course, astronomer, and he was really in love with this kind of mathematics, and he had his own theory of the universe. When he was a young man, basically explaining the universe, what at that time meant just the orbits of the 6 planets. And his equation was essentially 5 + 1 = 6. Because he took the 5 platonic solids and fitted them in kind of a model. You can do that in many different permutations. And he found one that up to like 5% accuracy gave the ratio of the size of the orbits of the planets. Now, it's a silly theory for many reasons. There are more planets, there are more solar systems, etc., etc. But the great thing is that he himself destroyed his own theory by careful observations. And Kepler, of course, is famous by observing that the planets do not move in circles, but in ellipses. And an ellipse is kind of an ugly circle. It's one that's squeezed on. And certainly it can have all kind of different shapes. And Kepler himself writes in his diary when he discovered this, I'm taking a horse cart full of manure into science. Because certainly his theory is very ugly. Now we think, no, it's absolutely beautiful because all these orbits are in fact explained in terms of mathematical figures. They're conical sections, and in fact there's a beautiful theory behind that. That's the classical mechanical, the orbits of classical mechanics that Brian explained, which go back to Newton. And so there's beautiful mathematics there. And in fact, the French astronomer Lagrange once said about Newton, no, he must be the luckiest man ever to live in the history of the planet because there's only one system of the world and he's the one who discovered it. So, very powerful statement. Now, of course, Newton did add that, and we should emphasize is that he really unified concepts because he unified the physics, the everyday physics, literally the falling apple with the movement of the planet. So in some sense, taking away the need of any kind of quintessence of fifth element describing the universe outside the planet Earth. Now, there are many, and I'm just skipping through that, just give you one example of a historical measurement which was the same kind of unification. It would be the 19th century equivalent of finding another particle. This is the discovery of infrared. I like the painting because it's painting something you can't see. It's actually Herschel measuring the temperature of light, first in the blue, then in the red, and then he puts the temperature outside the spectrum, the rainbow, and he measures that it's even hotter there. So it's a wonderful moment because certainly you see something that wasn't there before. And of course now we know that this rainbow, the colors of visible light, they stretch around this huge spectrum of electromagnetic waves. And so that's a terrific example of unification because all these things are just the same phenomena. In fact, electromagnetism, Brian explained some of it, is a great example of unification. These are the portraits of Maxwell and Faraday, and show them because actually I just recently saw these two small portraits that we still have. They actually are coming from Einstein's office. So if you wonder who were his heroes, actually it was Faraday and Maxwell that were hanging there, and he was looking at them every day, and I hope being inspired by that. Talking about Einstein, I think, and here I want to add some of the things that Brian talked about, which will be crucial for our further understanding. I want to kind of think of his contributions also as kind of a unification, namely unification of space and time. So let's go through this. And because that will be extremely crucial to understand the modern theories of particle physics. So one way to think about it is, so we want to understand this concept that time is an extra dimension, the fourth dimension. And I'm actually explaining this with a very simple example. So behind me, you see a movie. So these are just kind of two particles orbiting. And think of all the different stills, the pictures out of which this movie is made, and cut them apart and put them on a stack. So if you put them on a stack, you will see actually here on the left, we get the various pictures one by one, and we're moving up in the vertical dimension, which is time. And so clearly, this is the earlier pictures are on the bottom, the later pictures are on the top. And Einstein basically said, well, think of this not as space plus time, but think of this in this case as a three-dimensional material. Glue them together. So they can be one big solid object, which you see here on the right-hand side. And you see that what were the particles, the red and the green particle, they now became this kind of spaghetti strands going up. We call them world lines. And while we are sitting here, actually, each of us is forming this world line, going through space and time. Physicists actually look at the right-hand side as physical reality. It's space and time. You see basically the whole movie at once. You see the whole history of the particles at once. And it's diagrams like that that we want to draw and actually help us explain how modern theories are. Now, bringing you to the modern age, which is the age of particle physics, it's actually quite a challenge. So if you look at the pictures coming out of these accelerators, just this very thought that there is simple structure, there's a theoretical idea, there's mathematics underpinning this is pretty challenging. It looks like kind of garbage to the naked eye. And in fact, there were many times in the history of particle physics where people thought that perhaps it is. That nature is kind of a black box. You can see what comes in and what goes out, but you couldn't open it like modern electronics or something. And in fact, in the 1960s, this was one of the lines of thinking, kind of a holistic way of thinking that we're never to know, and we shouldn't even ask the question. Well, I would say in retrospect, that couldn't be kind of the worst point of view, because the box can be opened, and I like to say, inside the box is this little formula. So here I use the power of mathematical symbols to write down the formula, which essentially is the formula for the standard model. And that formula, you could give a lecture to mathematicians and they would understand each of these symbols. They might not understand the implication for physics, but all the symbols there, I would say, are beautiful, are elegant, and kind of make sense. Now, this is not really the formula that you get taught if you do a course in high-energy physics. I took a course in the Netherlands. Actually, I called that, the textbook we used the formula on the left-hand side. That's by Tini Veldman, the Nobel laureate. And he really wanted to emphasize, that there are many terms and it's hard work. Of course, it's hard work. But as you also see, now, basically the standard model can be put on a T-shirt. And that's an amazing achievement. You see these, of course now with Higgs added to it. 17 particles basically describing all of nature. That's a terrific achievement. And so one thing I want to get across, how? What are the ideas underpinning that theory? And to do so, and you should realize, by the way, that this is a book that you can get. That's the Book of Particle Physics. This would be the list of particles that people would have presented, for instance, in the 1960s, with all their properties. But in some sense, we want to describe. We not only want to describe the world around us, we also want to describe everything produced in these particle accelerators. And the fact that that simple formula explains that thick book, which is really like a telephone book of particle physics, is an amazing achievement.